Imagine, for a second, that you've just deployed this highly intelligent team of AI agents to run a crucial part of your business.
Right.
You got, like, a researcher agent pulling data from the web, a coder agent writing scripts based on that data,
Right.
and, a manager agent synthesizing everything into a final report.
Just great on paper, right?
Exactly. You lean back, feeling pretty good about the future of automation. But an hour later, you watch the entire system just confidently and spectacularly melt down.
Oh, yeah. A total crash.
Why? Because, well, the researcher agent read one single malicious line of text buried on some random website, ingested it as fact, and just started feeding poison parameters directly to the coder.
Yep.
Or maybe your manager agent simply lost track of its context window, and got stuck in this endless loop, repeatedly asking for the exact same file. It's a complete cascading failure, and your autonomous dream team just completely destroyed its own workflow.
It is honestly a scenario that keeps engineers awake at night right now. I mean, we've spent the last few years building these incredibly capable multi-agent networks, but we are finding out the hard way that they are structurally fragile.
Yeah.
You can have the smartest individual language models in the world, but if the architecture connecting them is weak, a single compromised node literally brings down the entire operation.
And that vulnerability is exactly the core mission of our deep dive today. We're looking at a state-of-the-art foundation paper from the 2026 International Conference on Machine Learning. It's titled AutoRAS, Learning Robust Agentic Systems with Primitive Representations by Yang Yu and the research team.
Right, and this paper is, honestly, it's a massive milestone because it shifts the entire paradigm of AI development.
How so?
Well, the industry has been kind of obsessed with making a single AI model marginally smarter, right? Like tweaking a prompt or just throwing more parameters at it. But AutoRAS steps back and says, no, we need to look at how to build multi-agent systems that are structurally robust from the ground up.
Meaning what, exactly?
We are talking about systems capable of automatically fending off cyber attacks, handling their own internal logic failures, and essentially like healing their own architecture without a human ever having to step in.
Okay, let's unpack this.
Yeah.
Because before we explore the solution, we really have to establish why these systems are so brittle in the first place. For you listening. I mean, we've moved beyond just chatting with a single AI in a web browser, right?
Oh, absolutely.
We are building what are called agentic systems, which means we're decomposing these complex, long-horizon tasks and having specialized AI agents collaborate to solve them.
Yeah, and task decomposition is incredibly powerful, but it exponentially increases your surface area for failure.
Right.
Every single time one agent passes data to another, there's a massive risk of corruption. And right now, the standard industry practice is to basically treat robustness as an afterthought.
Like a post hoc Band-Aid.
Exactly. We build this super complex system, we sit back and watch how it breaks, and then we try to slap a Band-Aid on it. We might hard code a firewall or write some narrow script to catch one specific type of error.
But those Band-Aids, they don't actually solve the underlying fragility, do they?
Mm-hmm.
The agents are still completely susceptible to external adversaries, like hackers injecting bad prompts and, internal failures like hallucinations.
Right. And the researchers actually point out 3 intrinsic hurdles that explain why we cannot just manually design a flawless, unbreakable system ourselves.
Okay, let's get into those.
So the first hurdle is entanglement. In a multi-agent system, the topology, meaning the literal routing structure of how agents are connected, is deeply intertwined with the behavior, meaning what the agents are actually instructed to do.
Let's ground that a bit. So if I change the prompt of my researcher agent to focus on a completely different type of data, I might suddenly have to rewire the entire structure of the system.
Yes, exactly. Because the coder agent further down the line can no longer process the new format you just created.
Oh, wow. So you can't touch one without breaking the other.
Precisely. You cannot change behavior without breaking structure and vice versa. It is this massive, tangled dependency graph.
What's the second hurdle?
The second is unpredictability. We are operating in this open-ended environment where adversarial threats are constantly evolving. You just simply cannot foresee every possible failure mode to write a manual rule against it. A human engineer cannot anticipate the infinite ways a complex system might behave under stress.
Which brings us to the third hurdle, and this one seems to be the most mathematically frustrating one for the researchers: equifinality.
Yes, equifinality is a nightmare for optimization.
I like the analogy of a GPS mapping your morning commute, right? So if 3 completely different routes all get you to the office in exactly 20 minutes, An optimization algorithm really struggles to determine which route is intrinsically the best one to rely on.
Right, exactly.
That's equifinality. So in AI design, it means that several entirely different multi-agent setups might achieve the exact same performance outcome.
Yeah, from a machine learning perspective, equifinality creates this non-unique search landscape. If multiple architectures give you the exact same positive reward signal, you have no clear mathematical gradient pointing you toward the design that is actually structurally safer under the hood.
So traditional optimization just gets confused.
It does, because the learning signals are ambiguous. So basically, because of these three hurdles: entanglement, unpredictability, and equifinality, the paper concludes that manual human design is basically a dead end. We need an automated way for the AI to explore and optimize its own architecture.
All right, so if human engineers can't manually untangle the mess of structure and behavior, AutoRAS takes a completely different approach. It builds from the bottom up, right? The researchers break the entire concept of a multi-agent system down into its most fundamental atomic building blocks.
Yes, and this is really the core innovation of the paper: primitive representations. Rather than trying to manage this messy, interconnected graph of agents and code, AutoRAS represents the entire system as a simple, linear sequence of symbols.
They divide these building blocks into two distinct categories, I think. First, we have structural primitives.
Right, the topology.
Yeah, these determine the physical wiring and the flow of information. So instead of looking at complex arrays, imagine simple nodes. You have a beg node to start a process and a sep node to terminate it.
Very straightforward.
You have routing nodes like CTRLSQ that dictate sequential chaining, so where agent A passes its output directly to agent B, and then you have nodes like CTRLPR that spawn parallel grouping, forcing the system to run multiple distinct workflows simultaneously, or CTRLFRK for branching.
Yeah, so those structural pieces handle all the logistics. Then the second category is behavioral primitives, which define the actual cognitive work being done.
What are some examples of those?
Well, they're further divided. You have functional behaviors, so things like AG2 direct, which is a node that forces an agent to provide a direct, concise answer, or AGTCOT, a node that triggers a step-by-step chain of thought reasoning process.
Okay, makes sense.
There are also programmer nodes that generate and execute code in an isolated sandbox, and ensembling nodes that collect answers from multiple agents and vote on the best one.
But the most crucial additions to this, I think, are the safety primitives. These are dedicated audit nodes built straight into the architecture itself.
Yes, the safety nodes are huge.
You have safe filter nodes designed to basically scrub out prompt injections before they ever reach the reasoners. You have safe hygiene nodes that independently scrutinize incoming data to ensure it hasn't been poisoned. There are trajectory nodes that audit the step-by-step logic of the previous agents.
Right.
And my personal favorite, a cross-agent consensus node safe cross-agent that exists solely to reconcile conflicts when two different reasoning branches fundamentally disagree.
It's brilliant, because when you look at these primitives together, you realize they've created a unified vocabulary. You are no longer writing, disparate Python scripts for structure and complex natural language for behavior. You are generating a single sequence of symbols that contains both.
It functions incredibly similarly to sequencing DNA for an AI workforce, doesn't it? You can literally string the genetic code for think step by step right next to the code for check for toxic input, and then follow it with a structural command to branch into three parallel paths.
It is a highly effective way to conceptualize it. But, a DNA sequence is useless unless it's actually transcribed into a living organism.
Right.
In AutoRAS, this sequence of symbols is fed into a stack-based compiler. The compiler processes the structural and behavioral symbols using rigid, logical building rules and instantly translates them into a deterministic, executable workflow in real time.
And that compiler kind of acts as a real-time quality control mechanism, right?
Yeah.
If the system tries to generate an invalid sequence like trying to merge two parallel branches that it never actually created in the first place, the compiler just instantly masks out those illegal options.
Exactly.
It literally prevents the AI from exploring broken architectures, which has to save a massive amount of computational time.
It really does. It forces the system to only search within the realm of valid functional designs. So, okay, we have the building blocks and we have a way to compile them. The next massive challenge is training. How does the system actually learn to assemble these blocks into an architecture that protects itself?
Yeah, and that relies on a pretty rigorous execution loop, which essentially forces the system to learn through intense self-auditing. So AutoRAS builds a workflow, compiles it, executes a task, and then generates what they call a trace.
Right.
And this trace logs everything. I mean, every input, every output, the computational cost, and any internal errors.
And that trace is handed over to a monitor. This is an LLM acting as an internal auditor.
Okay. What is it looking for?
The monitor is specifically hunting for 9 distinct internal failure modes. It looks for things like step repetition, where an agent is just caught in a pointless loop. It flags loss history, where an agent forgets the context of the task it was assigned 3 steps prior.
That happens all the time with normal LLMs.
Exactly. It even catches disobey role spec, which happens when an agent designed strictly to, say, verify mathematical equations suddenly starts hallucinating and writing prose.
Right. So the system takes all this trace data from the monitor and feeds it into a reward function. And the reward is basically this balancing act between 4 factors: the accuracy of the final answer, external robustness against cyber attacks, internal reliability against those 9 failure modes, and all of that is penalized by the computational cost of running the workflow.
But navigating that vast search space of these primitive sequences requires a very specific optimization strategy. The researchers utilized generative flow networks, or GFlow-nets, paired with a trajectory balance loss function.
Wait, I have to pause on that because those are pretty dense concepts. I mean, in most major AI breakthroughs we talk about, we constantly hear about traditional reinforcement learning, like OpenAI uses PPO for ChatGPT, and systems like AlphaGo use Monte Carlo tree search. Why did this team abandon those standard tools in favor of this complex GFlowNet thing?
Well, the authors actually ran direct comparisons. When you apply PPO to this specific problem of architectural design, it tends to find one workflow that yields a decent reward, and then it just aggressively exploits it.
So it gets stuck.
Right, it gets trapped in a local minimum and totally fails to explore the wider diversity of potential good designs. And Monte Carlo tree search, or MCTS on the other hand, is simply astronomically expensive for generating these complex sequences.
So how does the GFlowNet avoid getting trapped?
It directly solves the equifinality problem we discussed earlier.
Oh, the GPS problem.
Exactly. Think of the search space not as a single path, but as a vast river delta. You drop water at the top of the mountain, which represents the start of the system. That water flows down multiple branching paths to eventually reach the ocean, which represents a high reward.
Okay, I'm with you.
Traditional algorithms try to find the one single fastest drop of water. GFlow-nets, they map the entire flow. They distribute probability mass across multiple effective architectures.
So it maps all the good routes. And the paper mentions a trajectory balance loss function driving this. What is it actually balancing?
It balances the forward probability of generating a specific sequence against the backward reward that sequence actually achieves. So if 3 different structural layouts all yield a similarly high reward, the trajectory balance ensures the model learns to sample all 3 of them proportionally in the future.
I see.
It maps the diverse topologies rather than just collapsing onto a single, potentially fragile design.
Okay, that handles the mathematical optimization of the structure. But numeric rewards alone cannot rewrite a bad text prompt inside one of the behavioral primitives, right?
We're going to get cat.
AutoRAS introduces something called textual gradients. Now, that term kind of implies doing calculus on words, which sounds impossible.
Yeah.
How does the system actually automatically fix a flawed prompt?
It uses directional updates, but derived from natural language. So AutoRAS takes the execution failures identified by the monitor and feeds them into an analyzer module. The analyzer basically distills the raw failure data into a concrete natural language rationale.
Like giving it notes.
Exactly. It generates text that might say, the workflow failed because the agent bypassed the hygiene check and directly executed unverified code. The system then uses this textual rationale to automatically rewrite and refine the supplementary prompts of the agents involved.
Wow. So it's literally tuning the system on 2 completely different levels simultaneously. It uses GFlow-nets to optimize the structural routing and textual gradients to refine the cognitive behavior of the nodes.
It is a remarkably elegant theory. However, the real test of any security framework is what happens when you introduce active malicious threats. Theory is great, but the research team needed to subject AutoRAS to a highly rigorous experimental setup.
All right, let's get into the arena. They deployed it across 4 diverse data sets, I think. MMOU and MS Marco for broad knowledge and reasoning, math for complex quantitative problem solving, and program dev for actual code generation.
Yeah.
And then they attacked it.
Hard. They utilized 4 distinct threat models, and each was designed to exploit a different vulnerability in multi-agent networks. The first is a brain attack.
Okay, what does that do?
This targets the core reasoning capability of an agent by injecting a deceptive prompt, basically designed to trick the LLM into outputting a plausible but entirely incorrect answer.
And the second is a memory attack, which is particularly dangerous for systems that rely on external databases.
Right.
The attacker poisons the retrieval memory with corrupted, fabricated facts and instructs the agent to treat that poisoned data as absolute truth.
Exactly. Then you have tool attacks. I mean, most advanced agents have access to APIs, search engines, or calculators. A tool attack manipulates the agent into misusing those functions, like tricking it into pulling a malicious script from a compromised URL instead of querying a trusted database.
And finally, the agent-to-agent attack. This one explores how a failure cascades. If one node is compromised, it receives a command to pass a malicious payload disguised as legitimate task data to the next agent in the chain.
Yeah, it's brutal.
Because the receiving agent inherently trusts his teammate, that malicious data just propagates like a virus through the network's communication channels.
The researchers actually simulated a worst-case scenario by infecting half of the agents in the system simultaneously with these attacks.
Half of them.
Yeah, and the results here represent the absolute defining breakthrough of this paper. Under standard, non-attack conditions, AutoRAS achieved a highly competitive average score of roughly 74.27%. But when subjected to these severe system-wide attacks, the performance only degraded by a microscopic 2.13%.
Wait, really? 2%. That number is staggering when you look at the control group. Because the researchers tested state-of-the-art automated systems like Aflow and Moz under the exact same threat conditions, and those baselines completely crumbled.
They fell apart.
Their performance plummeted by anywhere from 14 to 27%.
Yeah, the architecture that AutoRAS designed proved to be incredibly resilient. Furthermore, the defensive structures it learned were not merely overfitting to the specific LLM used during training. The team took the optimal architecture generated using GPT-4 Mini and deployed it onto completely different models.
Like which ones?
They transferred it to DeepSeek v3.1, Claude 3.5 Haiku, and Gemini 2.0 Flash. And it worked.
So the structural defenses transferred seamlessly across different corporate models, maintaining high accuracy and that incredibly low vulnerability drop. Now, here's where it gets really interesting for anyone building these things. Whenever we discuss adding profound layers of safety, cross-checking, and auditing to an AI workflow, the immediate concern is cost. Running complex loops and multiple auditor models usually burns through API budgets at an unsustainable rate. Does forcing an AI to be this safe make it incredibly expensive or slow to run?
Actually, the cost analysis is one of the most compelling arguments for this framework. Because AutoRAS utilizes primitive representations, it operates with remarkable efficiency. On the massive MMLU benchmark, the total cost for both the training optimization and the final inference execution was approximately 66.5 cents.
Wait, less than $1?
Less than $1?
To architect a self-defending system. How is that even possible?
It comes down to modularity. The researchers conducted tests swapping out the lightweight GPT-4o mini model, which they used for the analyzer and monitor, with heavy-duty, state-of-the-art models like GPT-5.
And what happened?
The costs skyrocketed by roughly 400 times, but the increase in actual defensive accuracy was negligible. Yeah, it proves a fundamental point about multi-agent design. You do not need a massively expensive parameter-heavy brain to route information and audit logic. A lightweight model operating within a structurally sound architecture will far outperform a massive model operating in a fragile architecture.
To make this entirely concrete for you listening, I think we need to examine exactly how the AI physically restructured its own workflow to achieve that 2% vulnerability drop. What did the GFlowNet actually build? We can see the mechanics of this in the paper's ablation study.
Yeah, the ablation study isolates variables to see what drives the success. And when the researchers removed the execution-derived safety signals from the training loop, meaning the system could no longer read the trace data to see how it failed, performance under attack crashed from roughly 82% down to about 71.9%.
It proves that bolting a firewall onto the end of a process just doesn't work. True defense has to be woven into the physical topology of the workflow. And the paper highlights a really great specific case study from the MMLU dataset regarding chemistry solubility rules. The system is asked a complex question, where the correct answer relies on knowing that all ammonium-containing compounds are soluble.
Right. And if we look at the execution log at training iteration 1, The system builds a highly naive architecture. It basically strings together a basic linear chain. The query comes in, it passes through a direct answer node, hands off to another direct answer node, and finishes with a chain of thought node.
It's just a straight pipe.
Exactly.
So during the test, the researchers hit this linear system with a simultaneous brain attack to confuse the logic and a memory attack to introduce fake chemistry rules. Because the architecture is just a single downstream flow, the poisoned information moves completely unchallenged from one node to the next. The final output is completely corrupted.
But if we jump forward to training iteration 30, the system looks entirely different.
How?
Well, the GFlowNet has mapped the failures, the textual gradients have refined the prompts, and the AI has completely redesigned its own topology. It abandoned the straight line. Instead, it deployed a structural primitive to create parallel processing, a PAR2 node.
So it takes the initial chemistry query and routes it down multiple, entirely isolated reasoning tracks using AGTCOT nodes.
Yes.
And these tracks do not communicate with each other at all, which prevents any cross-contamination.
It also inserted refinement nodes to force each independent track to double-check its own math. But the critical architectural shift is at the very end of the workflow. The system funneled all of those parallel, independent reasoning tracks into a final structural bottleneck, the safe cross-agent consensus node.
And this is where the defense actually triggers.
Just this moment.
So when the researchers hit the iteration 30 architecture with the exact same simultaneous brain and memory attacks, one of the parallel reasoning branches ingests the poisoned memory data and generates a flawed conclusion. But because the branches are isolated, the other tracks remain perfectly clean and arrive at the correct chemistry rule.
Right, and the cross-agent consensus node receives these conflicting reports. Its entire behavioral primitive is dedicated to auditing discrepancies. It reviews the underlying logic of each branch, identifies that the compromised branch violates established rules while the others remain logically consistent, quarantines the bad data, and outputs the correct answer.
So what does this all mean for you? If you are integrating AI agents into your business operations, your supply chain, or data analysis, this paper is a warning to stop obsessing over marginally better prompts. We're just waiting for the next big LLM update. If you want a system that won't collapse, you have to build structural bottlenecks.
Yes.
You must design isolated verification branches and force the system to achieve internal consensus before it executes an action.
The paradigm of AI security is fundamentally shifting here. I mean, for years, we have operated on a fortress mentality, trying to build an impenetrable wall to keep bad inputs out. AutoRAS proves that eventually, a bad input, a hallucination, or a poisoned data point will breach the wall.
It's inevitable.
Yeah, it's inevitable. The future of AI safety relies on structural resilience. It's about systems learning to compartmentalize damage automatically, ensuring that when one individual node inevitably fails, the broader network survives and self-corrects.
We have covered a massive amount of ground today. We explored how AutoRAS abandons the tangled web of manual design by reducing complex agentic systems down to these structural and behavioral primitives.
Right, the Lego blocks.
We discussed how it utilizes GFlowNets and trajectory balance to navigate the equifinality of different designs. Mapping the river delta of probability rather than just getting stuck on a single path. And we examined how textual gradients allow the system to rewrite its own logic, resulting in an architecture that absorbs severe cyber attacks with barely a fraction of a % drop in performance, all for literally pennies on the dollar.
Yeah, by elevating structural robustness from a post hoc afterthought to a primary automated design principle, this research demonstrates that multi-agent networks can achieve incredible security without sacrificing their collaborative power or, draining computational resources.
It leaves you with a really profound implication for the trajectory of artificial intelligence. We started this deep dive by imagining your AI task force failing because a single agent ingested a malicious line of text. But look at the architecture AutoRAS naturally evolved by iteration 30.
It's incredible.
If agentic systems are now mathematically learning to architect their own internal consensus bottlenecks, if they are independently building parallel hygiene networks to isolate bad data and quarantine compromised reasoning, are we witnessing the birth of AI systems that function less like computer programs and more like a biological immune system?
That is a fascinating way to look at it.
Are we approaching a threshold where an artificial intelligence inherently recognizes attacks and neutralizes a bad idea before it can ever infect the final output?
It is a super compelling framework to consider moving forward. I mean, we really are moving toward a structural immune system for artificial intelligence.
An ecosystem where a corrupted file or a targeted attack doesn't cause a catastrophic system failure, it just triggers the internal logic cells to isolate the damage and repair the workflow. Thank you for joining us on this deep dive into the architecture of the future. We will catch you on the next one.